All right, folks. Hi, my name is Chris Ertel. I am currently on sabbatical. My last gig was head of engineering at GetThrough, where we did a lot of interesting things with SMS and MMS for nonprofits, political parties, democracy, etc. After the election, it was time to go, I will charitably say, reinvent myself. This brought me into the sort of orbit of NX, of AI, of ML, of these things in Elixir. And as impressed as I was with those things, especially NX, it occurred to me that it would be really cool to use NX for something that wasn't just ML, that wasn't just another attempt to do AI, wasn't just another thing with like LLMs or whatever. We have the ability to smash matrices together and do interesting things, and the scientific computing in the last 70 years has done interesting things with matrices. So why can't we do interesting things in Elixir? That's my rough thought, nice shower thought. So there's a disclaimer. Because of some of the subject matter in this talk, I am not your stock guy, right? I mean, I'll take your money, but I'm not your stock guy. I'm also not your structural engineer. I'm not a professional engineer. We're going to be touching on something that, like, if you squint at it, you might be like, I will build a bridge according to what Chris's code says. Please don't do that, and especially don't credit me if it does happen. The other thing I want to point out, and this is something I've been watching with some fascination, hearing various side conversations here. Who here has used AI in some capacity in the last, like, I would say 10 minutes, but like, let's say like recently in career or like hobby or something, right? Like hands? Okay, so a lot of hands, right? How many people have used it to earn money or in connection with their jobs? Any hands? Okay, and who here has used it in connection with giving a talk? All right, cool. So we're all learning this new frontier of stuff. I pushed this in some interesting places. I think that there will be some rough edges from this. I had to nix some things entirely because of just a mess that they have made. And so in this talk, I'm going to be talking about a few places where things just went bananas. My brand, I think, is going to be going forward like talks where I try to do something and fall flat on my face and then explain it to everybody else so that you can fall flat on some other more comfortable part of your body. So again, if you see anything wrong, just say I will tell you you're absolutely right. I've been modeling. I've learned. So we're going to be talking about three major things that we think we can do with matrices and with NX. We're going to be talking about doing some stuff with stonks. We're going to be talking about doing some things with in-body simulations, and I'll explain what those are a bit later. And then we'll also be talking about doing stuff with simulating trusses. So first question, we're going to be doing stonks. Who here has done anything with stonks? Stonks. Okay, just to be clear, right? Cool. Who here has like professionally done stuff with stocks? Fantastic. Nobody will. Oh well, I see you. You be quiet. Everybody else, just go along for the ride. It's going to be great. Okay, so the thing we want to do is we want to do some stock analysis, and I thought to myself, like, it would be really neat that you have time series data in the form of stocks. You have a stock ticker, so like, I don't know, Bed Bath & Beyond is like BBBY, Netflix is NFLX, I think, et cetera, et cetera. Purely random examples that won't show up later in this particular slide deck. And you can get the closing bell price at the end of the day. You could do intraday prices, you could do some other things. For my purposes, I just wanted to look at what the historic closing bell price was. So we're going to go into Livebook. We're going to pull in our normal stuff. We're going to grab some NX. We're going to grab some XLO. We're going to grab Rec. Rec is kind of the MVP for the first part of this because we have to go pull in stock data. So you can go and you can find different places online to pull down historical stock data. I use something called the Financial Model Prep. It's like FMP if you Google it. They offer a pretty solid API, and they have reasonable pricing tiers for reasonable sets of features. I particularly like the historical stuff. They've got it going back, I think, 25 or 30 years at my price, and it's like reasonable. One of the neat things about finance and fintech, if you pay them money, they will give you all kinds of things, and they're kind of adjusted for lots and lots of money. These folks are more like hobbyist money for what I'm doing with them. So what we do is we pick our tickers. The tickers that we are going to be looking at are going to be ExxonMobil, so ZOM, Shell, HAL, which is Halliburton, SLB. Does anybody know what SLB is? Schlumberger, all right. Love, Southwest, awesome. UIL, anybody? United, all right. They might even fly out properly today, we will see. And then Bed Bath & Beyond is BBY and Netflix. So the reason I picked these particular stocks, I wanted to go back over the last, I think like 8 years or something. There was this thing that happened in 2020 that caused a lot of stocks to do something really strange. And so I wanted to pick a window that was going to kind of reflect both that weirdness and then less weirdness. So with those stocks in hand, we go and then we issue a bunch of requests to the API at FPM and FMP, and then we get back a bunch of this data. Critically, we get this data back in reverse chronological order. I was not aware of this, and it caused problems for me. It spent me several hours of debugging for reasons I may get into later, depending on time. So if we have that, the first thing we want to do is make sure that we even got data that looks reasonable. So we go, we take that, and then we have to do a bunch of unpacking into Vega Lite, and then we're going to render it. This is kind of my first minor gripe. This is also the first time I did some serious work, what I would consider serious work with Livebook rather. There's a lot of like munging data, moving it in, moving it out, and it feels kind of clunky to me. I was really hoping that I could use something to get like, make a data frame and then move easily between data frames and tensors and Vega Lite. That has not been my experience that it is as seamless as I would like. I'm sure other people that are better than I am don't have this problem. For me, it always feels like a lot of song and dance. Does anybody else have like a similar issue, like doing lots of marshalling with these things? Okay, so it's just me, that's fine. Again. So if we do this, we get something that looks a lot like stonks. Things that are kind of neat, you can probably spot the aforementioned anomaly around 2020. Who knows what that could have been. And the other thing that we can see here that's kind of neat, and when we zoom in on a couple of stocks, it'll be more apparent. Some of these stocks are tightly correlated, some are not. So if you are an oil field services company, for example, Schlumberger or Halliburton, your business is a lot like the oil companies that you work with, so Exxon or Shell or whoever. If you're Netflix, you're doing your own thing. If you're a Bed Bath & Beyond, you're kind of doing your own thing. So later on, we're going to look at how well these stocks correlate with one another. So the two things that I thought would be kind of fun would be doing a simple moving average of some stocks. The SMA, simple moving average, is one of the most basic of what are known as technical indicators of a stock. Has anybody done like technical indicators on stocks? Okay, it's yet another way of chopping up the data and looking at the entrails and like the tea leaves and trying to decide how to make your money. Long story short. And then correlation between stocks is kind of interesting for me, both as an indicator and also just as a general sanity check of does my mental model for how these companies, or at least their prices, work together. So going into a little bit, an SMA is just a simple moving average. All we're doing is we're saying, I have a in-day SMA. I'm going to look at the current day and then back up to end days. I'm going to sum up all of their prices, and then I'm going to do just a normal average. The simple moving average is about as straightforward something as we can pick. I give you the explicit version of a 5-day version at the bottom there. There are more interesting ones. The EMA is a little bit more common, I think. That's the exponential moving average. That says that the days that are closer to us are going to be weighted higher than the days that are farther away. One of the other nice things about, I think, the EMA and possibly the SMA is that you can do them incrementally online because you can express like the next day in terms of previous days and some interesting weighting and things. For our purposes, we're just going to pretend we have all the data and do the analysis all at once. So this is pretty painless to do basically in Elixir. The thing that is a little weird is you need to go and build a chunk of the data and then kind of slide that. So you have days 1, 2, 3, 4, 5, then you want to look at days 2, 3, 4, 5, 6, then you want to look at days 3, 4, 5, 6, 7, et cetera, et cetera. This kind of begs an interesting question, which is what happens on day 4 of a 5-day moving average? And the answer that I've settled on, and I think most people settle on, is they just don't exist. So you have your kind of window size for the moving average, and then anything before that much of window size has come in, you just pretend doesn't exist because it's not well defined. So these are, again, kind of codes for doing this. And then finally, we go and we run it through our different stocks. And when we go to visualize it, we do pretty straightforward Vega Lite stuff. And this is what we get. when I first did this, all of my stuff was on the left side of the actual stock line. So the blue is the actual stock prices. You notice this is very noisy. And then the orange is the 5-day, and then the, 30-day, and then the red is the 90-day. SMAs should always be lagging indicators. That means they should almost always be to the right of your underlying data. All of mine were to the left. I was very puzzled about this. I found out that the reason for this was because I had the data was in the wrong order. The simplest way that you can think of to do that moving window with Elixir stuff, let me find the spot here, you end up grabbing the date of the last window, and if you the last data point, if you don't reverse it properly and do some other stuff, it will just come out wrong. And that's the importance of using Vega Lite to visualize this stuff, is you can inspect it and say, that doesn't look right at all. Generally, this is good. Sometimes it's a problem. So we saw the Elixir version of that is a lot of kind of munging, maps, reduces, enum shenanigans. And to kind of refer to the original version of that, we have this chunk every, and we have map, and that's awesome. NX actually just has window sum, so we actually have that tool built in, and we don't have to do anything clever about it. Provided we can get it into a tensor, we can then do these operations on the tensor. So that was a place where NX made my life easier. Where NX made my life less easy was that I had problems passing arguments into a def-in that were not tensors. And so you'll see around lines 2 and 3 there, I had to pass in a keyword thing. I had to say, hey, look, this is actually a keyword, pull out the window size, and then make it work. There are some rough edges. There are some rough edges in NX. I believe this to be one of them. I don't know if anybody else has had similar problems, but this is something that just felt kind of awkward to me. And I was talking with some colleagues about this, and I think it's because behind the scenes NX is doing a lot of compilation and other things, and it's not always obvious why it's doing what it's doing. And it's not always obvious which things are kind of programmer directed and then which things are just kind of weird macro magic. So my personal Elixir theory is that every time you use a macro, somebody just gets a little sadder. But I recognize that that's in some ways a minority opinion. Not a wrong one, but a minority opinion. So we're going to go, and this is that same routine with NX, and it works out perfectly cromulently. Previous graph looks the exact same. If they're wrong, they're both wrong in the same way, and that's a win as far as we're concerned as software engineers, right? So then I said, aha, okay, well, I want to look at correlations between stocks. So we did the SMA, that was pretty straightforward. So correlation between stocks, I'm going to use something called a Pearson's correlation coefficient. Has anybody here ever done statistics and knows what Pearson's is? Okay, cool. So again, be quiet, don't ruin for the rest of them, especially if I get it wrong. So the basic idea behind Pearson's is you have 2 data sets, and in our case we're using time series, and you want to say, when this data set changes, how does this other data set change? And is that always a positive relation, a negative relation, or are they basically unrelated as far as we can tell? And the Pearson coefficient will range between -1 for an inverse relationship. For example, the price of gas goes up and then the profits of airlines go down because gas is more expensive and, or we want to say that they correlate together. So for example, the price of oil goes up, so the price of oil services companies goes up as stocks go. And then you, of course, have theoretically no correlation, which is whatever the oil industry is doing, people are still watching Netflix, so whatever. So we go, and I'm highlighting this code mostly to show you that the math itself isn't too weird. I didn't typeset the equations for this because I didn't think it made a lot of sense by itself, so I kind of skipped that. But I do want to highlight that actually assembling this stuff is a little bit gnarly, especially in pure Elixir. And then graphing it, what was kind of fun with the graphing is that I made something called a lasagna plot. I've never heard of a lasagna plot. I didn't know that a word existed for this particular plot, but this is a lasagna plot. So, any Garfield fans? Yeah. So the thing that's kind of neat here is that we have this theory that some of these stocks do vary together, and sure enough, we see that Halliburton and Schlumberger and ExxonMobil all have a strong correlation with Shell. So Shell is our underlying stock. You'll see that on the y-axis label, that we're looking at how things vary with Shell's share price. We also see, kind of confirming our intuition, that Bed Bath & Beyond is kind of all over the place, and that Netflix is, again, kind of doing whatever it's going to do. One thing that I did that was a mistake in this is these are sequential windows. So we're looking at like the first 30 days, the next 30 days, the next 30 days. A better way of doing this would have been to do a sliding window, which is how we did the simple moving average, where we are just doing this kind of smeared out version. This, however, still proves my point when it confirms my hypothesis that these stocks do vary together. So we're happy about that. This comes out well. Except, we're going to move this into NX. And I thought this was a great idea. And unfortunately, I'm not very good at NX. But I know a large matrix that is good at NX, or so I thought, and that was Claude. Claude is not very good at NX, it turns out. In particular, Claude is very, very certain that certain functions exist as part of stock NX. For example, a covariance function. And it's so convinced about this that it kept using it. And I said, no, you can't use it, it's not there. And it was quite insistent that it was there. And then I went to the simple expedient of pasting the docs to it. And I said, no, in fact, it is not there the way you think it is. And it said, oh, you're absolutely right. And then it proceeded to get it wrong again. And so in frustration, I said, all right, well, we're just going to have to agree to disagree. Spoilers. Where did my talk go? Oh, it's hiding. There we go. And so the thing I want to stress there is that with NX, it was rough. And even once it had kind of grudgingly figured out how to use this, it still got the math wrong. It still had these problems. And so my experience at this point in the adventure has been that it will hallucinate things still for NX, and I suspect that's because there's actually not a lot of training data for NX out there. And also that you have to double check what it thinks it's doing. So the next one that I tried to do, so we've done stonks. Let's do in-bodies. And so in-body simulations, these are kind of one of your classic, maybe undergrad, maybe at a fancier level graduate math things. And it's basically simulating piles of little sticky points, like little points, let's say, I don't know, a galaxy, little sticky points like planets. And you are trying to simulate gravity between them. And so the useful thing about this is that you have all of these points and the force of gravity between each one. So I have 2 point masses, let's say M1 and M2. Maybe you could also think of this as like the sun and the earth, right? Or, I don't know, me and like, well, any 4 of my dogs, right, clumped together with enough gravity. So you take the mass of those 2 points, and then you multiply that by g, which is the gravitational constant. You can pick that to make your simulation look good. Don't tell your professor that, they'll get sad, but you pick g to make your simulations look good. And then all of that goes over the distance between the points squared. So this is an inverse relationship. Basically, as things get farther away, it very quickly drops off the influence. So the gravitational pull between like me and Bruce right now, because Bruce is there, is much more rather than between me and Isaac in the backpack. So this is the only actual physics you need to know. Okay, slight lie. So there's a little more physics, a very small amount more physics. So as Newton showed us, the acceleration on a body, the force on a body equals the mass times the acceleration. We can rearrange that. The acceleration of a body is equal to the force divided by the mass of the body. All this says is for the same shove, a heavier thing will move less than a lighter thing. So we can also go and we can play with that math as well. We say, okay, the acceleration of body 1, we take that, F, the force of gravity from body 2 on it, we divide it by that, by the mass of body 1, we find the force, and eventually we get to the acceleration on the first body is just the gravitational constant times the mass of the second body all over the distance between the two. This is fine. Now, I lost a step in there. So one of the things that is missing from this is that it's not actually just F equals ma, it's actually the sum of the forces equals the mass times acceleration. So it's not just one body, it's all of the bodies acting on a single body. So what we can do with that is we can sum it, and then we can simulate an entire solar system of things. The way we simulate those things is that they have an initial position, x naught, and then we're going to figure out the new x based on the initial position, and we're going to integrate all of the velocity, which is x prime there. I apologize to anybody that actually cares about mathematical notation. I've gotten a little sloppy on this, but this is the basic punchline. Velocity, x prime, follows the same rule. You have x naught prime, which is your initial velocity, like what speed you're initially going in, and then you add to it your acceleration, x double prime, integrated by time, and then that gives you your final velocity. Again, exact same style of math. Out of curiosity, who here has seen an integral in the last like 5 years? Right. So we're doing what we can here. And the way that we do this in the computer is with something called explicit Euler integration. And all we're doing there is we're saying, you know, you have your initial position, and then you add to it your velocity times your timestamp dt. And this is the first way you would attempt to solve this problem. It follows almost directly from these equations. You love it. Unfortunately, it starts to have artifacts. And in particular, if dt is very small, it might not work. If dt is very large, it will overshoot and do crazy things. So when you're actually trying to use these methods, explicit Euler is like okay for games, and even then it's a little shaky, but you really want to do something better, and we'll talk about better in a second. So again, as we mentioned before, you have multiple bodies, and we're going to go ahead and we need to sum up all of those forces, and then that will get us to the final acceleration on a body. And here's the fully worked version. If I have 1 point mass, it's going to be the sum of all of the masses of the other bodies that interact with it divided by their distance to that body. So this is kind of what that looks like. And if you're looking at that and you're thinking that looks a lot like a reduce kind of, you're thinking in the right direction. So we're going to go ahead and we have some data structures for this. For our points, we have their position, we have their mass, we have an ID, which we use for some bookkeeping later, and then we have the acceleration and the velocity. So x and y, ax and ay, and then bx and by, and their mass. We go ahead, we're going to initialize this by basically just throwing them onto the kitchen table, and they're just going to scatter everywhere. And for the very first one of them, the ID is 1 in that case. We're going to make it just super heavy because that will let us do some interesting things. We go ahead, and this is how we update our position for the point. You know, we see that exact Euler there is your, you know, x plus your timestamp scaled, et cetera, for x and y and bx and by. Now, this is where we actually start pulling in the forces. So in this case, we're going to go and we're going to map over all of our bodies. We're going to then accumulate forces. So when we think accumulating forces, we say accumulate, we think reduce, and we do the same thing. And then we have this bit here on line 9, which says, hey, if it's me, I'm not doing any forces on me. So we're just, you know, if it's not me, we'll actually do the calculations. Otherwise, we're going to throw up our hands and ignore it. And then we pull out the delta, the dx and the dy. So there's the differences on the x and y axis. And then you calculate the actual distance that that represents. You use that to calculate the force, and you're pretty much all set. You'll notice that there is no sine or cosine in here. There kind of is if you squint at it. So 16 and 17, those right-hand sides of the dx over r and the dy over r are, trust me, equivalent to sines and cosines like you would expect if you were doing this otherwise. Now, when we actually go to run this, we step through it, works fine. But again, we know that that integration method is fundamentally flawed. That Euler, explicit Euler is going to have problems. So in the late 1960s, a person named Verlet, who was doing these sorts of simulations, came up with a better way of doing it. And you basically offset a little bit. So you update your velocity half the way, you do your position update, and then you update your velocity the rest of the way. And when you do this, it actually makes it really stable. And it did so well that it took another like 15 or 20 years for us to actually figure out why it worked very well. I refer you to the Wikipedia articles on Verlet integration and you know, the actual proof of why it works. The most flippant answer is it keeps you from having distortions in phase space, and that probably, it meant nothing to me when I first learned about it until I did more reading. So if you're curious, that's your homework assignment, figure out why Verlet is better than explicit Euler. So the demo of this, very quickly, is anybody here epileptic? Good. If not, free diagnosis. So, I'm sorry, that was awful. So this is our live book, and we're going to run this. And I apologize for Firefox's SVG engine, and I also apologize for Livebook, and I only slightly apologize for the code. So ignore the frame buffer that's broken and flashing behind it. But if you look here, you should see some of these points are just hanging out there. So like we've got our little traveler in the upper right-hand corner just kind of floating off in space. But you notice we've actually accumulated some orbiting particles. Does anybody see like the little orbiting dudes next to the big red dot? All right, so cool. We did a solar system. Awesome. We can be pretty happy about that. So this is good. We are pleased with this. The thing is, this is all piles of points, and that feels like something we should be able to parallelize. And in fact, we can. So we're going to go and we're going to move from what is called an array of structs. So that is a collection of all of those little points, and I used records in the earlier implementation. But now we're going to instead have what's known as a struct of arrays, and that's usually what you want for numeric stuff. So we now are going to have a map that has a collection of tensors, and then we have one big tensor for all the x positions, one big tensor for all the y positions, et cetera, et cetera. When you're doing numerics, you typically want to do structures of arrays because that is more ergonomic for the computer anyway. This is what our acceleration looks like using NX. And this is where I have kind of a pet peeve with NX again. And that is that sometimes it does something very helpful in terms of rewriting what look like scalar terms. So for example, lines like 14 and 16, those variables, we're just doing math. And the math is very clear. It's very clean what it is, but it's not obvious to me as a user whether that is, we're bodging vectors and matrices together or scalars. That's a personal preference. I don't think there's anything wrong about it. Earlier parts, I was more explicit. So if you look at lines like 7 and 8, you see that we actually call into NX to do things. So again, we're kind of doing that same basic setup of the different steps and then kind of alternating, we do half our acceleration, then we do our position update, then we do the rest of our acceleration. And this is, so that's accumulating the forces. The next one was the acceleration steps. And again, it's kind of that same thing. The math is nice and clean. I find that I like the NX approach because it looks more like the math. This is good. I don't like it as much for reasons, well, that I'll get into. So when I run this on my laptop, and I have not debugged whether this is my bad NX code, Claude's bad NX code, or my own incompetence in setting up a laptop. This is not running NVIDIA. I've got to try this on my workstation at home with actual NVIDIA GPUs in it. It might behave better. This will run correctly approximately once, correctly. Then it will run 100 times slower. And you'll see the point like think and then kind of like move again, and then if you reset it, it runs 100 times again slower, so it's basically just stopped. And I'm pretty sure that's due to something I'm doing wrong in terms of maybe not clearing out NX properly between runs or something else. I don't know what it is, but it doesn't behave, whereas the naive Elixir implementation did behave. So one of my personal areas of exploration is going to be figuring out why that is, what went wrong, and how I can fix it. So the third thing I wanted to look at is trusses. And here is something that we're going to have a little bit of fun with this. And in particular, this is a hard problem. So the idea behind a truss is that if you, who here has ever looked at a bridge? Okay. I go for the easy ones. Don't look at me like that. I go for the easy ones. Or you look at, if you go look at the inside of this building on the atrium here, you'll see all of these steel beams connecting everything. So to mechanical and civil engineers, those are known as trusses. So the important thing about those is you can think of them as, who here has ever played with Tinker Toys? Okay, awesome, remember Tinker Toys, or erector sets even? Okay, cool. So you have the what we call members. So think beams. That's going to be your like 2x4s, or if you're on a bridge, like big old steel I-beams or whatever. And then you have where they connect, and we're going to think of those as nodes. The interesting things that we care about for our purposes are that members don't actually bend. This is a flagrant lie in real life, but go with me here. Members don't bend. When they connect to nodes, we don't have to worry about what are called moments and this means that we also don't have to worry about kind of weird, crazy deformations. And that lets us use something in math called the small angle approximation. And that basically means that to simulate a bridge, we can use matrices, hand wave, everything will be fine. And we're only going to worry about loads on each of the nodes, which is where the beams connect to each other. We're not going to worry about loads distributed across beams, because if you do that, then you introduce the concept of bending moments on the beams, and you get back to bending beams, and we said that beams don't bend, so we're not going to do that. So this entire problem can be simplified to basically this matrix. On the left-hand side, you have the forces acting on the nodes. In the middle, you have K, which is your stiffness matrix, which is a way of encoding all of the springiness, for lack of a better way of putting it, of all of your members. And then you have U, which is the actual displacements of your beams. The reason we care about the displacements is, who here has heard of Hooke's law? Okay, so the idea is that you have, when you have a spring, it's at rest. When you pull it out a little bit, when you have a displacement, it's going to react with a force, usually negative kx, I think. So it varies directly with, the more you stretch it, the more force it tries to restore itself with. So there's a lot of moving parts in this, but the basic idea is that for a given beam member, truss member, we say that the springiness of it is equal to the Young's modulus, which is the elasticity of the thing. So for example, rubber has a high elasticity. Diamond has a very low elasticity. Oddly enough, the similar property of water is only like 10 times less compressible than, more compressible than diamond. So that's why in other parts of engineering, we pretend that water cannot be compressed. That's a whole other thing. And then we have the A, which is the cross-sectional area. If you imagine a big rubber cylinder, if it's skinny, right, it's going to be easier to use as a little floppy noodle. If it's big and thick, it's going to resist a lot of movement. And then finally, the length of the member. So the longer it is, the more it's going to behave a certain way. So when we go to implements in Elixir, we're going to have some data structures, for nodes, for members, for all the different parts. And where it gets weird is that we have to do some transforms. One of the biggest problems with this particular method is you have this matrix where you have one row per degree of freedom for a node. A node can move on the X and the Y, so that's 2 degrees of freedom per node. More complicated models will have more degrees of freedom. And you have to encode this stuff. Building that matrix is a pain in the neck. It's even more of a pain in the neck when you look at your beam and you have to account for, like, it's rotated at an angle, and you have to turn it from this local coordinate system to the global coordinate system. So that's kind of what this starts to do. This one in particular says, okay, my definition of a beam is what connects two nodes and what its elasticity is. So we have to actually back out its own coordinates and its angle from, knowing what the nodes values are, then we back out those properties for the member. So that's the code that does that. We figure out its kind of local stiffness, and then we start to build our actual transforms, and then finally start assembling the matrix. The thing that I want to highlight on this is that most of the work here is actually going to be just building the different matrices and vectors to represent the problem. We do something called a boundary condition. So you can imagine that if you build a bridge and you just drop it on the floor, it's like, bump, all right, it's on the floor, whatever. To make a bridge useful, you have to actually anchor it to either side of something. And when you anchor it, you say, by definition, these 2 points that we're anchoring it with shouldn't be moving. If you have a bridge's anchor points moved, you have a problem. So in math, we refer to this as a boundary condition. It's saying that, like, look, I don't care what the rest of the function is doing. At this point, at the very left side or the very right side, it is not allowed to move. So we have to apply that. And we do this by zeroing out various parts of the matrix and then making a couple of other changes. And then finally, to actually solve it, it's like 2 lines. It's a very straightforward linear system. You have your force vector on the left-hand side, you have your springiness matrix on the right-hand side, and you have it doing the displacements, and you can basically just call solve directly. You can calculate the forces in the members, and then finally, we can actually show you what this looks like. So all of that kind of, I know there's a lot of hand waving there. This is what we get. So this is our truss, and it's what's called a Warren truss, and we have it sitting there. We have a single point in the middle that is bearing a weight of 10 kilonewtons, and when we run that, we're going to see that all the blue members are in compression, all of the red members are in tension. So the blue members on top, they're getting kind of squished together because it's like bending in, and then on the bottom, they are going to be kind of pulling apart because it's spreading out. Now, when I was first doing this, I didn't believe this result. I figured that either I or Claude had made a mistake because I'd run it a couple of times, and it defeated my intuitions because on a normal perfect plate, the top should always be in compression. When you're pushing down, the bottom should always be in tension. This is why we use rebar to reinforce concrete decks. So I said, this is clearly wrong. So I did what any good engineer would do, and I went to other packages that I didn't implement and said, okay, what is your solution? It got the same solution. So it turned out that my intuitions were completely incorrect, and that the robot was correct. And so that was a little hurtful, but I'm glad we got there in the end. So first, I want to thank everybody for your time going through this with me. Second, I think that there is a lot of potential for using NX for things that aren't just AI. I know I perhaps didn't articulate that as well as I could have, but hopefully these have spurred you to some ideas of neat problems we can solve that aren't AI. And then also, finally, I'd just like to say that this is my first really AI-assisted talk, and this is my first time using AI to actually help with what I consider more engineering code. And the thing I want to point out that's kind of interesting to me is that for the earlier parts of this, the stock analysis, the actual moving average work, even the rough high-level idea of using the Pearson's correlation, that was myself, that was easy, Wikipedia, and then using some work from Claude to help with the live view, the live book actual, showing stuff, visualization, that's the word. When I went to do the truss stuff, I remembered I had done this in undergrad 15 odd years ago, and so I leaned more heavily on Claude. And God help me, it basically one-shot that truss analysis, which I thought was really interesting. It got it almost completely correct. The one thing I got wrong was some minor rendering quirks. But the actual core analysis, it did fine with. And to me, that's really interesting that we have these tools available. And I'd like to just kind of urge everybody to try to push yourself outside of the tools that you're used to using and the problems that you're used to using, because all of us now have access to these really neat little gizmos that can help us. In some cases, they'll also hurt us. See some of those slides of, yeah, that didn't work at all, that was terrible. But we're definitely on the ground floor of a lot of change. So thank you again.